So good morning, everyone. Let's start with the Smart Energy Management Part 2. The first presenter is Mohan Gandhi with the paper ECOQUBE Driven Smart Data Center. I'm gonna open, sorry.
Hello, everyone. Can I? Okay. Sorry, Mohan couldn't be here. This is Cagatay from Lande. I'm the project coordinator of EcoQUBE project. Today, I will be talking about the usage of artificial intelligence as a management system, especially focused on coolant system on data centers. So everyone might be actually questioning what I'm doing here at Black Sheep in between all the individuals, experts who are dedicated to raise energy efficiency, and I'm representing a power-hungry market. But we know the fact that it has to change. So. We are just willing to make it happen. I would like to start with pointing out the challenges and the state of the art in the market right now. All the emerging technologies that we use today, including Industry 4.0, 5G, artificial intelligence, your Netflix accounts, and so on, they basically require wider band connection, and they require lower latency, and of course for industrial applications especially, they require enhanced security. So it is of course an energy penalty. Everybody in the industry, they started carrying their workloads to the cloud, where it's way more efficient and you require less stuff, so it's easier to maintain and lower initial investments as well. But depending on the conditions that I mentioned before, the requirement of lower latency and faster connections and broader band, there is a new paradigm entering in our life. This is edge computing, and edge computing is actually a globally distributed computing paradigm, where you bring computing and data closer to the end users to deliver especially lowest latencies. So what we foresee that it's going to be responsible for more than 10% of the data center energy consumption in a closed feature. And what we also see generally in data centers, 40% of the energy consumption is definitely related to the coolant system, and we have to actually take a look at this consumption and make it reduced. So here comes our first challenge. If you bring data centers closer to the end users, let's say each 1 kilometer's diameter, then you are facing with the cooling system's efficiency in different climates. Like you have to be energy efficient in Istanbul, Rome, and Stockholm as well. So this is not the only challenge that we are facing right now. The rack power density has boosted up, literally leveled up in the last decade, and from 3s we are reaching an average of 8 right now. So yes, we have to face with the external conditions, climate, and we also have to face the internal power density, the waste heat that we are producing nowadays. And even though we are facing with these two big challenges, we can also tell that most of the data center users, the managers, they are not using precise cooling systems, which is actually affecting the energy efficiency of data centers drastically. So the conventional data center cooling systems are basically focused on keeping data center inlet temperatures in a strict and interval, and they do not actually evaluate the cooling performance and their effect on the IT devices. How they usually work, they rely on some thermal probes, some digital thermometers, and their all decision-making system is based on some sensor reading, and they actually do not evaluate the IT systems performance. Among all, European Commission said, okay, we have to change everything. By 2050, we have to be climate neutral, and by 2030, we have to reduce the emissions by 55%. But then they also said, okay, this is not valid for ICT and data centers. They are already consuming a lot, and we have to make them energy efficient by 2030. So this is actually putting a lot of pressure and responsibility on our shoulders. So what we have done with ECOQUBE project, basically we are introducing preventive strategies and supportive strategies to the market. Preventive strategies are focused on reducing the energy consumption in data centers, and supportive strategies are trying to supply the energy consumed by data centers with minimum carbon footprint. If we focus on these two strategies step by step, the preventive strategies, I'm not going to be modest here. We are changing the market a lot. We are changing the system, decision-making systems within the data centers into a sensor-driven version to big data-driven version. We basically listen your data centers, all your active components, and we evaluate your data center not by only some temperature readings, but some KPIs such as power usage effectiveness ratio, primary energy savings, CO2 savings, renewable energy factor, and so on. So at the end of the day, we are giving you some the great prescription regarding to your data center's needs. Plus, we use open source CFD, computational fluid dynamic simulations to be able to deliver the best airflow for your data centers for both your energy efficiency measures and as an energy efficiency measure, and also for the best performance of your IT devices. This is another challenge just jumps in this stage, because most of the data centers are utilized between 11 to 14%, which means that I'm always describing it like you have a garage of cars, and they are all working. Some of them are going really fast, really inefficient. Some of them are just working, the engine is working, not going anywhere but consuming energy. And some of them actually going at their most energy efficient state. This is basically the same for data centers. Usually all the components within a data center, both IT components and coolant systems, they all work all together, but nobody actually is tracking their efficiency as a big picture here. So how we are addressing this challenge in ECOQUBE project, we are making smart scheduling. We are not randomly sending the workloads within the data center, but we have a three-dimensional, we call it zonal heat management system, a three-dimensional heat management map. We are deciding this is basically the decision-making authority for our coolant systems, but for our virtualization system as well. So we basically tell altogether, it is an artificial intelligence augmented coolant system. This system is basically orchestrating, it's a holistic system, orchestrating both hardware and software systems, as I mentioned, making a three-dimensional map, controlling the coolant system to provide the best airflow for the best energy efficiency and performance, plus not randomly sending the workloads within a data center, but orchestrating the workloads to make data centers, to keep the data centers at their most energy efficient state. You can consider it that way. You have the servers, you have the best airflow, but still it's not going to be enough for some energy hungry servers. So we basically take the load from them and equally distribute the loads and shut down all the unnecessary IT equipment and cooling system as well. And the supportive strategies, this is a long story, and a lot of experts are talking about it here today. What I can tell, this is basically the best way of integration to microgrids. This is what European Commission focused of the call of ECOQUBE project. They wanted us to make small data centers, and we call it edge computing here, more integrated into buildings or districts, energy management and cooling systems. This is given great advantages to data centers, for especially small data centers. They can benefit from the building's coolant system. They can actually send their waste heat to the heating system of the building or district. And this is drastically reducing the initial investments to operate a data center. You can cut down many investments at the beginning stage, as a, let's say the creation of the white space. Plus, if you can integrate the data centers into the energy efficient energy management systems of the building, then you can actually cut from your UPS expenses and basically all the other expenses related to your uptime management. So we received 3 million euro funding from European Commission to deliver the outcomes of ECOQUBE project. Our consortium consists of 11 companies from 6 different European Union countries, as well as Turkey. We have universities, some laboratories, some profit-making organizations like Lande. And all together with the combined effort, we are working to deliver ECOQUBE's outcomes as promised. So we have a really simple roadmap. We are developing, as I mentioned, the artificial intelligence augmented holistic management system. I'm taking one step ahead after Coolant. We believe that this will be the future of data center infrastructure management systems. We want to reduce energy consumption by 20% and CO2 emissions by 20%. And I think it's going to be interesting for everyone. We're going to deliver 3 guidelines. We will guide end users to use open source CFD applications, and we're going to have an open source CFD analysis for edge computing systems guideline. We have a green energy management system for edge computing applications guideline, and at the end of the day, we will deliver an energy efficiency guideline for edge data centers. This is going to be similar to EU Code of Conduct data centers, which is also aiming the same thing, but this is not for hyperscale data centers, but this will be only dedicated to smaller edge data centers. So if you are interested in the results of ECOQUBE project, I would suggest you to follow us on our webpage or social media accounts, and there is a link to ECOQUBE's newspaper that you will be introduced by the news and the outcomes of ECOQUBE project. And if you have any other questions, on the right QR code, you can find my email and you can reach me for your questions. I'm all done. If you have some questions, just feel free to hit. Welcome. Please.
I have a question. Could you explain which CFD simulations are you using in your project?
The question was which CFD simulations we are using for ECOQUBE project. We actually focus on OpenFOAM because it is an open source CFD analyzing approach, which is also allowing us to deliver our own solvers, because most of the, I know of the commercial solvers, the CFD softwares, they are working really good, but they're also limiting you. And I shouldn't tell it right now because it is not really ready yet, but we are actually developing some solvers which are giving better solutions for smaller data centers. So if you just follow our newspaper, we will step by step inform you about how we are making it. Welcome. Thank you so much.
Okay, so I will try to give you access to the software. And now let's go ahead with the second presentation. The speaker is Djaffar Ould Abdeslam, and the presentation is Smart Meter, Inclusive SME Artificial Intelligence for Proactive Energy Management by End Users. Okay.
As I see, he is not here now.
Sorry?
As I see, or he's offline. Okay, I got it.
The presentation is this one. Okay.
Hello, everyone. I am pleased to be here to present this project, SMI project. The SMI project, Smart Meter Inclusive, is co-financed by the European Union through the European Regional Development Fund in the Upper Rhine InteReg 5A program, as well as by the Swiss Confederation and the cantons of Basel-Stadt and Basel-Land, Basel and Arago. This project, with a total of nearly 2 million euros, involves, as you can see in this map, 15 academic and industrial partners. It's led by the ERIMAS laboratory of the University of Haute Alsace in France. The photo shows the partner at the project launch meeting in Milhouse in France in October 2018. The background of the project, we can summarize it in this sentence: if you cannot measure it, you cannot improve it. This common management saying also holds true for the area of energy efficiency. Without a clear understanding of their energy usage, consumers are unable to take steps to reduce their consumption. The project is, of course, multidisciplinary and addresses the following aspects: social, legal, environmental, and technical. The objectives of the project are listed here and are naturally multidisciplinary. I will focus a little bit more of the part dealing with artificial intelligence. We can see the different objectives of the project. First, mapping smart meters and their types in order to have a clear and precise understanding of the existing potential in the Upper Rhine. The Upper Rhine region is the region of the east of France, Alsace, and the west south of Germany, but with the Baden-Württemberg region, or Lande, and Basel and the region of Basel in Switzerland. The second objective is undertake a general public survey to understand what are the barriers for smart meters deployment. The point I will more detail here is to design a new artificial intelligence enabled and secure smart meter. We have another objective, which is improve the security level of a smart meter. This point will be presented by Ivan in the next presentation. Another objective is the modification and harmonization of the current legal framework for the smart meter. And finally, elaboration of a white paper in 3 languages, French, German, and English, of course. The research questions and the challenges we have in the advanced, we can say for the advanced power meters, or so-called smart meters, they work in real time. They can measure in real-time consumption. They can save energy around 15% and manage the demand side. But the drawback is no automatic data processing for decision-making. For the smart meter we develop in this project, we want to link artificial intelligence and micro-societal analysis for decision-making and design a laboratory prototype, I will show it here, that will communicate with the power meters, the existing power meters of utility companies. Monitoring energy consumption needs clear understanding of the energy usage and activity. This one is the first step for the artificial intelligence embedded smart meter. We can see here this in this figure the some devices, and at the
left, the electricity meter, the existing one we have. If we want to measure the consumption of each device, we need to use an intrusive load monitoring. This one is using an individual sensor for each appliances, of course, which is difficult and expensive to do. But with the non-intrusive load monitoring, the idea of this one is to use, I can take the pointer, another pointer. Here we can use the NELM, non-intrusive monitoring, from one point measurement coupled to the electricity meter, and we can have a map of each device and the consumption of each device. This, of course, idea is not invented by us. It's existing as the Hart, who is invented first this idea, and it is used from like 14 years. I will show you, of course, what is the innovation of our part. The analogy of the non-intrusive mode monitoring is equivalent of the weight light decomposition through the prism. You have one consumption, and you can deduce and the individual consumptions of the loads. This is the prototype we developed. This is a version 2. We have now version 4. We use a device we developed in the lab, and we can use it like this. This SMI will be placed after the power meter. It will be able to disaggregate and control loads, control PV, batteries, and electrical vehicle by prediction of the production and the consumption. The artificial intelligence will interact with the user to learn from his habits and propose better solutions to optimize the energy. All processed data will be stored locally and remain the property of the user, because the artificial intelligence is inside the smart meter. What we can do to improve the artificial intelligence for learning, which is the biggest issue, of course, for the artificial intelligence, is to have a large database for learning. Google's chief scientist, Peter Norving, says, "We don't have a better algorithm than anyone else. We just have more data." Artificial intelligence needs big data for better decision making. For this reason, we build the household power electrical devices in the hardware in the loop, in the Opal RT in our case, simulator real digital time digital simulator. By using real time, we have this one in our lab. The objective is to create several scenarios very close to reality and construct a big database. We can test the final artificial intelligence algorithm in easier conditions. I can show you the video for an example in the lab for disaggregating the small devices. If it starts, I will off the pointer. Okay, it works. You can see, for example, the desk lamp blank 2. We make on. It's detected by the smart meter, and off is also. We have small delay, of course, in this case, because we use here the Raspberry Pi hardware. Hot hair gun off is detected also. Hair dryer on detected and off. After that, another desk lamp, gray color, is on detected, off detected also. And finally, milling machine. In this case, you see as the small consumption, it is more difficult than the big consumption, like, for example, washing machine or, yeah. This project was invited for general presentations, for example, in a virtual event on artificial intelligence in France, organized by the region of Baden-Württemberg in Germany, International Agency for International Economic and Scientific Cooperation in March 2021, and the 360 Grand Est, 3016 Grand Est region in the east of France, smart grids put digital intelligence at the service of optimizing energy management in December 2020. And we are invited for the visit of State Secretary Dr. André Baumann, the representative of the state of Baden-Württemberg to the federal government, and State Secretary at the Ministry of State in Stuttgart in Freiburg 2020. In the EUCOR, the campus, the European campus at the University of Freiburg in 2020. Finally, we would like to thank our funding partners, the InteGRIDy program, of course. We also thank EUCOR, European Campus, European Regional Development Fund, and the Swiss Confederation, the cantons in Switzerland of Basel City, Basel Country, and Arago. Thank you for your listening. There are questions?
Okay, I will be first. I'm just wondering, like, if the loads are identical, really small to each other.
So you can just repeat, please.
If the loads are identical, like, similar machines, like, I'm just questioning, like, how successful we are.
Of course, good question. We use also not only the, I don't talk, of course, about the technical part, but I can show you some articles we have. We use the power active, but we use the harmonics also to disaggregate. With the active power, you can see the levels. If the levels are similar, as you mentioned, what we have here with the devices we tested in the lab, we use the harmonics because we use it by our fingerprint of each device, because all the devices use the non-linear loads, and generally they are different. It's very hard. The reason we use also artificial intelligence and very advanced signal processing techniques, not only fast Fourier transform, but what we called also Stockwell transform, which works on the frequency and time domain. And with that, we can disaggregate more better.
If you want to try your technology in a more challenging environment like data center,
Yes, of course. Thank you.
Thanks a lot for the
Okay.
very interesting presentation.
Thank you.
You are in when you're in the PowerPoint. Let me show you.
Yeah, go ahead.
No, go to the PowerPoint.
Okay. So the next one should be, let me check.
No, this one is open.
Yeah.
You were in like presenter mode,
Okay.
but like presenter rehearsal mode, so it wasn't full screen. If you go to display settings, that's you, right?
Yeah.
So display settings will be, I don't know where it is. Here, let me do a test from downstairs and I'll show you. You should be able to see display settings.
So
Here, I can show you from when I see it downstairs. I'm gonna go put my audio on right now.
okay. So what are we are gonna do? I'm gonna present the next speaker.
Yeah, but let's fix this first, okay?
Okay. Okay. So we are fixing a problem, and then I will leave the floor to Ivan Rigoev. So just 2 minutes.
Okay. So when you go to your PowerPoint and go to presenter mode, okay, yeah. So here I'm not seeing full screen. I see something that says show taskbar, display settings, end slideshow.
Ah, okay.
And you want to click display settings. Do you see that on the top? Yeah, right there. Swap presenter view. Yeah, exactly.
Okay, sorry.
All right.
Okay, perfect.
Good. I'm gonna go. Thanks.
Thanks, Zia.
Can I test your sound? Oh wait, hold on. Yep. Can I test your sound?
Perfect.
Okay. Good. Thanks, Alessandro.
Thank you. So, okay. The next speaker will be Ivan Rigoev with practical security analysis of German smart metering system. So,
Can I share my screen?
yeah, probably now you can share your screen by clicking here.
So is it in full screen mode now?
Yeah, yes.
Okay, perfect. Hello, my name is Ivan Rigoev, and I work as a scientific researcher in Offenburg University. Today, currently I work on Internet project.
Sorry, Ivan, can you increase the voice because we hear you very, yeah. Better.
Without microphone. You hear me?
Yes.
Hello?
Yes, we can hear you.
Is it possible to hear me? Is it good work now or not? Is it possible to hear me or not? Please write in chat or do something.
Sorry. Ivan, we are hearing you.
You hear me?
Yeah.
Okay, perfect.
Yeah, now
Sorry,
it's okay.
because I think we have some problems with my phone. Currently, I work on Interact project, Smart Meter Inclusive, and Djaffar already present our project today, so I will not spend time on it now. Our team is responsible for work package 4, security concepts for distributed smart grids, which includes 2 main tasks. We should make a comparative security analysis of rules, regulations, and architecture to find potential attack vectors and check it on our work package 4.2 semi-solution penetration testing. For this purpose, we got a number of smart metering devices, but in current presentation, we will discuss only 2 left one devices. Is German BCI smart meter gateways from Feb and Connexa and PPC. Both smart meter gateways currently connected to test PKI infrastructure, but firmware at these smart meter gateways is the same with devices that used in production. BCI, it's a German Federal Office for Information Security, and unlike France, in Germany exists a number of electricity supply and distribution companies, and to cover all requirements and find same time and at the same time ensure security, BCI creates documentation that fully describes SMI solution architecture, protocols, and possible communication scenarios. Every smart meter gateway manufacturer must certificate smart meter gateway according to BCI documentation before starting with devices realization. The main part of German BCI system is smart meter gateway, or SMGW. It's a device that connects 3 different isolated from each other networks: local meteorological network, or LMN, home area network, or HAN, and wide area network, or WAN. Local meteorological network is used to connect energy, gas, and heat meters to smart meter gateway. Home area network is used to connect controllable local systems such as home appliances to smart meter gateway, and wide area network is used to connect smart meter gateway with outside world. The left side of this slide shows macroarchitecture of German SMI system. Usually, smart meter gateway use mobile communication to connect to the outside world, but also exist solutions that use Ethernet as one port. But in practice, they are less common. Commonly, smart meter gateway installation presented at the right side of the slide with small blue and white boxes smart meter gateway, and that is installed on EMH smart meter chassis and connected to smart meter gateway local meteorological network via white wire that comes out from top right part of smart meter gateway. The most important participant in PCI SMI system is gateway administrator. Gateway administrator installs firmware updates and access control policy, or ACP, that determines how often and which data will be sent to external market participants. In the German system exist two types of data: billing data and anonymized data that is used to check network status by the grid operator. Commonly, billing data sent one time per month, and anonymized data every 15 minutes, but it could be tuned by smart meter gateway administrator via installing different ACP. WAN and HAN connection should be protected via TLS protocol version 1.2 with a strict list of used chaper suites. And also important moment is that smart meter gateway should not responding on wide area network incoming connections before smart meter gateway will get a special wake up package from smart meter gateway administrator. Scheme of data anonymization mechanism presented at the bottom right side of the slide. Anonymization data mechanism based on cryptographic message syntax that can be represented as a box with some number of fields. Meter sends consumption data to smart meter gateway. Smart meter gateway encrypt is with a special key that could be decrypted only by service provider, and synced with energy user data. After that, data sending to gateway operator who removes smart meter gateway signature with user ID, but could not got consumption data, and send it to service provider who can make analysis based on this data. In home area network, smart meter gateway produce three main functions: device diagnostics for the technician in the home communication scenario number one, getting consumption data by smart meter gateway user in home communication scenario number two, and possibility to control home appliances or other controllable local system that is implemented as a transparent SOC 5 proxy connection with certificate notification mechanism that is additionally protected via TLS. With scenarios described in home communication scenarios from 3 to 5, and the only difference is that connection initiator in case of 3 is a controllable local system, in case 4 is external market participant, and in case 5 smart meter gateway. In case of HAN security testing, we try to make SOC 5 to attempt our authentication methods, test common TLS server vulnerabilities, and apply fuzzing technique, but I will say later about results. In local meteorological network, smart meter could be connected to smart meter gateway via 3 different options: wired, uni, and bidirectional wireless M-bus. In case of bidirectional communication, it is protected via TLS, like in case of HAN and WAN connections. And in case of wireless M-bus, communication can be bidirectional and unidirectional. In case of bidirectional communication, it's also protected via TLS, and in case of unidirectional, used ISCBC plus CMAC to protect this communication. In local meteorological networks, smart meter gateway should be possible to act both as a TLS server and TLS client to make communication possible. Currently in LMN, we tested only wired network and did not find any vulnerabilities. The only interesting moment is using of uncommon realization of HDLC protocol, where sequence of fields differs from HDLC RFC. Currently, we're also trying to apply phasing technique also for element connection to find some possibility of consumption data tampering. As I mentioned from previous slides, all three smart meter gateway network protected via TLS protocol. And just a few words about TLS. TLS is a client-server protocol that implements authenticity, confidentiality, and integrity check mechanisms to provide end-to-end security. In common life, we meet TLS every day. This protocol is used to protect internet connection to banks, shops, and social networks. You could understand that your current connection is TLS protected if you see a padlock picture near website address or HTTPS in current website link, where S letter means secured. Because of TLS protocol complicity, different implementation vulnerabilities have been found several times now, such as Headbleed, TLS Poodle, or Padding Oracle. Due to TLS protocol widespread, it becomes more and more difficult to find new vulnerabilities, and one of the most effective instruments to find new vulnerabilities is fuzzing. Every protocol, including TLS, have some fields with a certain length and data types. During fuzzing, we're trying to mutate original data from this field. That means that, for example, we can try to put in 8 bytes length field 10 bytes of data, and sometimes it work and some unexpected things happen with TLS servers, such as deny of service, for example, or accepting wrong communication parameters via TLS server on client. During testing, we tried to use existing fuzzing instruments such as Java TLS attacker, but we found that they do not work with our smart meter gateways because of additional undocumented security mechanisms. During fuzzing, smart meter gateway simply stopped to responding to requests, and TLS server port switched to TCP wrapped condition, but the rest of smart meter gateway services continued to work. Only reboot helped to return smart meter gateway into a normal state and continue our fuzzing. One more problem of existing fuzzer software is that it is complicated to discover that TLS server do something wrong. For example, deny of service state is easy to be discovered, but in cases when the smart meter gateway, for example, accepts some wrong parameters that should not be accepted, it is much more complicated. Because existing TLS fuzzing software could not work with smart meter gateway, we decided to make our own fuzzer based on my colleague Andreas Wall's research. The differential fuzzing approach based on the idea that wrong work of some TLS implementation could be found via send the same requests at the number of different TLS server implementation, and after that compare the responses. If responses from some of the servers are not the same with another one, that means that probably behavior of some of the servers is incorrect, and this is required to do additional research. One more advantage of my colleague's fuzzing approach is bigger TLS server source code coverage, which can be detected by comparison of number of distinct responses from using the same number of requests for different implementations of TLS server.
Ivan, you have just another minute.
Okay, no
Sorry.
problem. That's enough. One more problem is that we cannot get smart meter gateways firmware without registering as a smart meter gateway administrator, and that complicated and required certification. Knowing that smart meter gateway TLS server implementation name and version is important for run it locally to improve fuzzing speed and get possibility to use address sanitizer that allows to make RAM memory analyze. Exists a lot of software and materials that allows to fingerprinting client-side TLS, but TLS server fingerprinting is much more complicated. To solve the problem, we made a tool that is also based on my colleague's approach. In this case, we sent a mutated client hello messages to a bunch of different versions TLS implementation and comparing with responses. Implementation that responds more similarity to implementation under test with more probability have the same version. So during test, we discover that PPC smart meter gateway in home area network use TLS server implementation GNU TLS with version 3.7. something, have open port with working SSH server with public key and password authentication that probably should be used by service technician. Got list of users that can be authenticated via with SSH and check this vulnerability at the same version of SSH service at my Raspberry Pi and tried to brute force passport for these users, but unfortunately unsuccessfully. In case of Connexus smart meter gateway, we discover that home area network TLS server have additional fuzzing protection. Use some embed TLS version 2.7. something to 2.24. something. It have documented SOX5 for communication scenario 3 that accept only uncommon authentication secure socket layer for SOX version 5. Also, we found that in home area networks, smart meter gateway use the self-signature certificate for TLS connection. That means that potentially nothing stops from sniffing of username and password from smart meter gateway consumption data service if attacker intrude to local network. Also, we currently work on managing the middle attacks on one network. Especially for this, we use CMW500 as a Feng mobile network base station to connect smart meter gateway, one interface, and sniff data. We know that smart meter gateway should not respond on any one connection before some GEW will get special wake-up package. This attack will not allow to tamper or decrypt data because of TLS public infrastructure, but probably we could find some vulnerability in one TLS implementation later and use it. One more vector of our future work is checking of smart meter gateway firewall that protects connection between officially connected controllable local system and external market participants. If it's vulnerable, this connection theoretically could be used to intrude to external market participant network. And as a conclusion, all currently found vulnerabilities belong to the system's information disclosure. So currently we did not find remote code execution or data tampering vulnerabilities. Consumption data sniffing in home area network is possible only when hackers intrude a local network. And it is also important to mention that this testing will not be effective at production devices because smart meter gateway write logs for every connection attempt and send it to smart meter gateway administrator. So in case if real hacker will try to make the same research, he will be founded very fast. So both PPC and Connexus smart meter gateway devices could be considered as secure at the current moment of our research. Thank you for your interest. That's all for me.
Thanks a lot, Ivan, for the very interesting presentation. We are a bit running behind the schedule, so there is no time for questions. But if you want to ask questions to Ivan, you can write the question on the Q&A or in the chat of the application.
Yes,
I'm sorry, Ivan, but
read it.
we are a bit behind the schedule. Thanks a lot again. So now is the time. The next speaker is Daniel Shangov with Smart 5 Grid, demonstration of 5G solution for smart energy grid of the future.
So hello, can you hear me?
Yes, we can hear you. You can share your presentation.
Yeah, okay. Well, the share button doesn't seem to be available. It's in gray.
That's strange. What I can do to save time is that I can share my screen,
Yeah, okay. Now it's
and
working.
you can say,
Now I
okay.
guess it's working already.
Okay, better. Okay.
So you can see the presentation now.
Yes, we can.
Okay. So my name is Daniel Shangov. I'm working for the electricity system operator project management expert, and I'm part of the consortium involved in these projects. Actually, the Smart 5 grid concept is based on the challenges faced with the new system topology presented by the penetration of renewables, the diffused and distributed generation, the demand side management, the prosumer concept, and all the paradigm which is posed by the new communication challenges faced by the industrial application of distribution and, of course, transmission networks. Now, as you know, as you probably know, most of the transmission network operation operates based on wire bound communication using, for example, fiber optic or fiber optic, or of course conductor-based frequency carrier communication, which is then separated from the 50 hertz frequency by line traps at the substations. So that's the basic technology. But now with the new challenges, new low latency, high reliability communication is needed, which also makes the highly demanding requirements of industrial standards. And this Smart 5 grid project it's all about that, researching the possibilities to use 5G communication for industrial applications. And for that purpose, I just shortly will make just a short presentation of main idea of this project, then the 4 use cases, which are based on previous PPP or public-private partnership projects under Horizon 2020. And then we are trying to outline the main outcomes and goals that we are pursuing with this project. Now, as you can see, there are 13 small, medium-sized enterprises involved in this project, 2 transmission system operators, the Greek one, ADMIA, and Bulgarian electricity system operator, which I am representing. Also, we have a university and the distribution companies, and of course, telecoms involved in this project. This is the geographic area and the main parameters in terms of finance and continuation of this project. Now, before talking about the use cases that are involved here, let me just introduce you the main concept that we are pursuing here. Now you have the on the left side, you can see the traditional power grid, in which you can see the one direction approach of energy from the power station through the high voltage substation, through medium to high voltage power lines to medium voltage substation. Then you have the distribution grid and the final consumers, industrial or household consumers. And then the communication concept here on the right side implies the 5-SMI grid solution, which also involves multiple direction of data transfer from aggregators on the low voltage grid to medium voltage grid, as well as from the high voltage generation. So here the data management needs to face all these challenges posed by the distributed and diffused generation, including behind the meter. And that's why we, of course, without denying the traditional optic and line communication, we also need to investigate the possibilities of a flexible, easier to deploy and cost-efficient and highly reliable and fast communication network, which is also proposes, let's say, flexibility services for such as, for example, frequency management, demand response, active and reactive power control, and etc. And also based on network slicings and edge computing, cloud-based solutions, and so forth. So the main purpose of this project is actually to develop a platform, an open source platform, which consists of open source repository, verification and validation framework, and also management and orchestration layer, which includes all the management orchestration functionalities connecting the whole system together. So as a basic concept is for the third parties, small and medium enterprises, and also all participants in the energy vertical, starting from generation through distribution and to industrial and end consumers, to be able to test, develop, test, validate, and upgrade and update the new network applications or NetApp. So what is a NetApp? A NetApp is a chain of functions that are executing a certain flexibility service. For example, voltage monitoring or active power monitoring, or cosinus phi, or power factor monitoring, harmonics, and so on. So these applications, in this case, we'll be simulating for our project, for the Smart 5 Grid project. As I mentioned, there are 4 use cases. So the network application, or the net apps, that will be developed, tested, run, and validated in this platform, using, for example, mainly hardware in the loop demonstrations and emulation of real-time data. I mean the data that are coming in real time by real energy infrastructure, such as, for example, voltage transformer, current transformers, of the substation, relay protections, and automation equipment, and other devices and sensors at the substation level, and also coming from the renewables, power electronics, and inverters. So these signals will basically be emulated via hardware in the loop and tested in a simulated part of the grid infrastructures, without, of course, doing any damage to the real infrastructure. So the basic architecture of the Smart 5 Grid project consists of 3 main layers, as you can see. First one is the energy infrastructure, all the equipment which will be feeding the data into the platform. I also gave some examples of such equipment. Then we have the telecommunication infrastructure, which will actually be the interface between the platform and the platform and the energy and infrastructure. So as I mentioned, the platform that we are developing now consists of verification and validation framework, open source repository, and the necessary interfaces, and also the management and orchestration network with all the controllers that run and operate the entire life cycle of NetApps and all the network applications. And we also have of the bottom layer of this NVF or telecom infrastructure, we have network function visualization, MEC computing, and telecom infrastructure. So MEC stands for multi-access edge computing. So as you can see, there are a lot of interfaces here to enable this.
Daniel, you have just 5 minutes left.
Yeah, okay. So let me skip these interfaces, just give you a short idea of the interoperability. The whole platform, as I mentioned, covers the entire energy vertical, starting from generation, transmission, distribution network, distributed energy generation, and consumer premises. And also, so we have the process zone, meaning that operational zone, which includes processes, field, station, operation, enterprise, and market aspects. And these are the all layers that we are developing on the communication platform, on the 5G communication platform. So the use cases that we are, the main objectives, as I already touched upon this, is to specify the critical architectural technological enhancements for the previous 5G PPP phases, and then to create the general system requirements for the baseline system architecture interfaces, also to define the system requirements for a fully featured 5G network platform, customized for smart energy distribution grids, but not only for the distribution aspect is involved here, but also transmission and the entire energy vertical. Then once we have this platform, is to develop 4 application NetApps and for 4 use cases to test and validate them, and then based on these results and the KPIs that are included in this project, we will be moving to the next step, which is standardization. So here are the use cases, 4 use cases, as I mentioned: automated fault detection on self-healing and distribution grids. This is the NL demonstration, which is based in Italy. The use case 2 is improving safety of maintenance workers in high voltage substation by use of intelligence cameras and wearable sensors. Here, the aim of this use case is to make to take the safety of workers to the next level, and also to optimize the cost for maintenance and of high voltage equipment at substation level. Then you have the use case 3 and 4, which is use case 3, millisecond level monitoring of distributed renewable based power generation resources, and also wide area monitoring. This is the use case that involves the Bulgarian and the Greek transmission system operators, and this use case monitors various parameters of the power line interconnector between these 2 countries. So
you have 1 minute left.
Okay, 1 minute left. The 4 use cases that I mentioned are now in a very early stage of development still, but what we aim is to enable ultra reliable low latency communication, network slicings, massive machine type communications, and to minimize the average systems downtime, and also the custom average interruption duration index. Of course, this project also has security and market aspects, including the flexibility elements, flexibility services that will be enhanced and enabled by using wide range frequency of 5G communication and the related security protocols to augment and to expand the already available fiber optic and wire-bound capabilities of this system. And also, it will set up a new market for third parties, small and medium enterprises, and also, on the other hand, but also it will set up new opportunities for power companies, from the whole energy sector to run, validate, test, and operate their network applications for flexibility services using a open source platform, which with all the inherent advantages, including the security and also the real-time data that will be used for emulations, making the use cases even more practical and relevant for the new challenges posed by the distributed generation and renewable sources that are coming in at different levels of the grid. So basically that wraps it up.
Daniel,
Yes, that's wrap. This is
I need to stop you because we are out of time. Just if you want to do a very quick conclusion.
Yeah, the very quick conclusion will be that it is an enabler for all interested parties and stakeholders in the energy vertical, and also third parties outside the energy vertical, such as telecom operators, ITC developers, and startups to run and test applications, different network applications related to the energy sector in a safe and reliable manner, which also dependable coming out with dependable results from this. So, if you thanks for your attention, and please you can follow us our site for more details. I see that it's a short time to present everything here, but if you are interested, you can contact us and check out our website and all the places that you can find it on the network.
Thanks, Daniel, for the very interesting presentation. If you have a question, you can again send the questions on the Q&A of the application or send a private message to Daniel. Thanks again.
Thank you.
Go ahead with the next presenter. The next speaker is Giovanni Tardioli with the presentation on innovative modeling approach based on building physics and machine learning for the prediction of indoor thermal comfort in an office building.
Hi everyone, can you hear me fine?
Yes, very well.
Okay. Thank you very much, Alessandro, for the introduction. First of all, let's start speaking about the iBecam research project. iBecam, which is the funding source of the paper we are presenting here today. So our iBecam has several objectives. First of all, to streamline the process of building control while keep energy expenditure to a minimum and comfort for the occupant at maximum level. Also enabling additional services such as car sharing for the building. It is based on several layers, but the main concept is the virtual building management system as a software as a service. There are three main layers, the building layers where we have monitoring plus actionable control, the science or intelligent layer, but basically it's focused on the building physics and machine learning for predictive control of the building, plus a service layer where we expose additional services for the building, such as retrofit design, fault detection, optimization of control, and commuting management. The project has made four main pilot case: an office building in Dublin, the IES headquarters in Scotland, an elderly care center in Italy, and the World Trade Center in Grenoble, France. There are already some key output of this project, such as the development of automatic calibration, plus the use of co-simulation between machine learning and building physics simulation, the use of virtual sensor for indoor environmental quality assessment. So for those of you interested in the project, I will suggest to get in touch or go to the poster section where you will find out more. So under this project today, I'm presenting a paper entitled An Innovative Modeling Approach Based on Building Physics Machine Learning for the Prediction of Indoor Thermal Comfort in an Office Building. So in recent years, the thematics related to thermal comfort and indoor environmental quality gained a lot of attention due to the introduction of new standards and normatives that put these thematics at the center of building design and control and operation. So also from a research point of view, many studies attest the importance of having high levels of indoor environmental quality as driving factor of many aspects related to the occupants, such as wellness, quality of life, productivity. For office building, generally I like to reference the 1990 rule that attested that 1% of the cost of companies is related to energy, 9% is generally related to building rental cost, 90% is associated with cost of personnel. So you can see that reduction in terms of productivity of personnel has a huge impact on the cost of companies. There are some problems when it comes to evaluating thermal comfort using normative methods such as the PMV methods. Generally, these methods are based on physics-based approaches that focus on a subset of physics variables such as air temperature, air speed, or relative humidity. However, recent studies attested that there are additional variables that needs to be taken into account for evaluating thermal comfort, such as psychological factor, age, gender, background, ethnicity, personal preferences, and so on. So recently, researchers started to look into alternative methods to predict thermal comfort that generally are based on direct feedback or the use of machine learning. So in this paper, we would like to underline three main objectives. First of all, the use of machine learning to predict thermal comfort in an office building. Combine the use of machine learning with physics dynamic simulation to generate a subset of additional variables for the training of machine learning, plus establish a comparison between the machine learning prediction and the normative methods. The methodology I'm using is based mostly on two concepts, a physics-based modeling and data-driven modeling. The physics-based modeling requires the creation of baseline model of the building, a process of calibration to create a high fidelity representation of the actual building. On the other side, on the data-driven modeling, first of all, there is a collection of feedback from the users in terms of thermal comfort, then the training of the machine learning and deployment of the machine learning model. And finally, there is a co-simulation approach to exchange data between the machine learning and the dynamic simulation software to generate scenarios assessments for control strategies. In terms of physics-based modeling, we are using a methodology that is formed by three major phases. First one, the creation of baseline model with gathering data from the actual building case study, then going to an operational model with injection of the actual sensor measurement into the building energy model, and finally use some advanced techniques, some sensitivity analysis and optimization to fine-tune the building energy model and reduce even more the gap between the actual building and the digital twin. So we are testing this in a research center in France from CEA called the ELOS building close to Chambéry. On the data-driven modeling side of things, first of all, there is a deployment of an app that the user can interact with to submit thermal comfort votes plus sets of additional variables. And we store this data and then we develop three main machine learning models, a simplified one just to predict if the user will feel cold or hot, a detailed one that uses a 7-value scale with reference to the ASHRAE standard, several state-of-the-art machine learning models, and a continuous scale between two extreme cold and hot, and that is based on a Bayesian regression modeling. One of the key elements of this research was the ability to combine together the actual measurements from the building plus feedback with a series of variables extracted from the building energy model. So we do this with the assumption that the calibrated model is a good representation of the thermodynamics of each room. So in each room, we are able, first of all, to extract sensor data, feedback, but also look at the simulation side of things, extract a lot many other variables such as operative temperatures, mean radiant temperatures, surface temperatures, and so on. All of this will go and enrich the set of predictors for the machine learning model. Some results in terms of model calibration. On the first phase, the manual approach, we already reached good values in terms of calibration with a mean absolute error on average of 2 degrees, while the CO2 level error was about 150 to 200 part per million. We went even further using optimization method to minimize these errors. So with the fine tuning, this graph represents the process of optimization of the error, minimization of the error. So we start from the triangle in each room, which is the starting baseline model. We optimize the model, try to minimize the two objective functions, and you can see the behavior of the optimization through the different iterations. This is the effect on the doing optimization on the model with a reduction of the error. The blue bar represents the baseline model before optimization. The green ones, the optimized model with a substantial reduction of the error at the end of the process. For validation here, we are presenting the time series values coming out of the sensor measurement in the building and the one extrapolated from the building energy model. You can see that there is a quite good representation in terms of thermodynamic behavior in each room. In terms of data modeling results, we got some good results, especially for the simplified method with an accuracy of about 85%. The detailed model predicted with an accuracy of about 70%, while the continuous modeling, the most challenging one, allow us to put together a graph similar to the one you see at the bottom here, where we can relate the accuracy to the the error acceptance. So, for example, if we accept an error on the thermal comfort scale of about plus or minus 0.4, we are confident that the model accuracy of about 75%. Here there is a comparison of the true vote coming from the occupants, the true vote compared to the PMV evaluation, and the true vote compared to the machine learning. So you can see that the PMV generally tends to overpredict, especially in mid-season. Plus, is not able to inform really well when the people feel cold in the office. While the machine learning can capture this, does not overpredict mid-season. However, has some limitation for extreme cases such as summertime, where the training points were relatively small. So for this reason, the accuracy of the model was a bit lower in this area. Is another result coming from the comparison. So the green dotted lines represent the true vote from the occupants. The red one, the PMV method, and the blue lines, the prediction of the Bayesian model. You can see that generally the range predicted by the machine learning model can predict quite well the true vote from the occupants, while the PMV for this mid-season condition tends to overpredict the thermal sensation. So as conclusion, we tested that using the machine learning models, we can improve the accuracy of thermal comfort prediction of about 25% compared to normative methods. The use of a calibrated model can be used basically to extract additional variables for training of the machine learning models. Also, the use of co-simulation strategies allow to generate dynamic results in terms of thermal comfort, and so can be used for scenario evaluation of comfort strategies. So that was it. Thank you very much for the attention, and I'll be happy to answer any questions. Thanks.
So thanks a lot, Giovanni, for your very interesting presentation. There is a very quick questions regarding the presentation.
Sure.
Question? No, there are no questions. But anyway, if you have some question, you can write on the question and answer again. And sorry, Giovanni, but we are a bit running behind the schedule, so we have to go ahead. Thanks again for the presentation.
Thank you. Thank you.
So the last presenter for this session is Tariq Ahmed, probably, or Bjarnhedinn Gudlaugsson, with the presentation implementation of renewable energy and smart solution technologies to pre-existing energy system, a cost-benefit analysis case study, InteGRIDy. You can share your presentation. Sorry. Okay, yes. We cannot hear you. No. You should. We cannot hear you very well. I don't know if you have a problem with the microphone or. No. I'm sorry. We cannot hear you. Sorry. I don't know if it is a problem with your microphone. If you could use another microphone or the laptop one. Did you check if your microphone is open or closed? Because we cannot hear anything. You can. Okay. Okay. Click on hide here. Okay.
Hear me?
Yes, now we can hear you.
Right. Okay. Right. So can you see my screen though?
No. You should share your screen. Otherwise, I can share mine, and you can say, I don't know, next slide. Okay. Now it's fine. Yes. I can see.
Right. Right. Okay. So, well, actually, my colleague Bjarnhedinn is supposed to make this presentation.
Okay.
So I haven't actually prepared that much for the presentation, but because he's having some problem with his mic, we can't hear him. I don't know why. I'll just go through it.
Okay.
So this, first of all, thank you, of course, for giving us the opportunity to make this presentation, which would be on implementation of renewable energy and smart solution technologies to pre-existing energy systems. So this is part of a work that we've done with InteGRIDy, which is an EU Horizon project. In the first part of this session in the morning, we had a presentation from Chris. So this is the second part, which deals with the cost-benefit analysis. So it's a case study, as I've mentioned, for InteGRIDy. Right. So in terms of the problem statement, well, first of all, the implementation of smart and renewable energy technology and pre-existing energy systems has the opportunity, of course, to provide beneficial economic gains to the internal stakeholders, such as, of course, energy system operators, alongside achieving other additional improvements in terms of environmental as well as social aspects. As such, the analysis focused on examining a number of pilot sites, monetize cost and economic benefits in order to highlight the economic benefits obtained from the implementation of smart solutions as well as renewable energy technology. So this is probably the problem statement for this particular work. However, in terms of the general project, which is the InteGRIDy, well, the project aims to actually integrate cutting-edge technologies, solutions, and mechanisms in a framework of replicable tools in order to connect existing energy networks with diverse stakeholders in order to facilitate optimal and dynamic operations for the distribution grid, fostering the stability and coordination of distributed energy resources, and also enabling collaborative storage schemes with an increasing share of renewables. So that's the main objective of the whole project, the InteGRIDy project. So for this work, we look at two different pilot sites, which is the Barcelona pilot site and then the Saint-Jean in France. So for both the two cases, we looked at two different scenarios. The first scenario, which is scenario A, is in the case of the Barcelona, it's a conventional energy system. So this is, the scenario without the implementation of any smart solution. And the same applies to the Saint-Jean as well. So this is based on assumption that the energy supply from pre-existing energy systems only comes from conventional fossil energy resources without any localized energy technology. And then, of course, the second scenario, which is in this case scenario B, for the Barcelona, that deals with smart solution implementation, which includes PV with battery storage technology and also integrated energy platform that deals with the participation in the electricity market as well as flexibility provider to the grid. Now, this is in addition to the conventional energy system. And for the case of the Saint-Jean, it's based around the introduction as well as implementation of renewable energy technologies, as well as smart technology solutions to pre-existing energy systems from the initial case, which is a baseline. So in terms of the approach which we've used for this analysis, first of all, we, as I've mentioned, is part of an InteGRIDy of a much bigger project. So we obtain inputs from other work packages. This in particular is work package 8.4, which deals with the cost benefit and life cycle assessment. So we get input from those other work packages, which of course we had a lot of engagement with the stakeholders in, first of all, trying to identify key performance indicators which are applicable to the cost benefit analysis, and then, of course, the data collection, which also deals with a lot of stakeholder engagement, because once we identify those set of KPIs, we then need to identify the set of data that we need in order to be able to calculate those different KPIs. And of course, the second stage deals also with the data validation and the cleaning, and also carrying out the CBA calculations. And then, of course, the final stage deals with the CBA calculations, which at the same time also deals with a lot of stakeholder engagement, because whatever all the analysis that we do, we have meetings with this stakeholders and show them the result that we obtain, and make sure that they are happy with what we're getting in terms of the analysis, and of course finally the results and the outcomes. So some of the inputs that we've used, the data input and the indicators, is shown in this table. So inputs such as the average cost of energy, cost of energy consumption, the energy payback time, the energy imports, the renewable energy, rest generations, and share of renewables, and energy prices, and so on. So this is just a typical example of some of the inputs and indicators that we've used for the CBA analysis. In terms of the results, so as I've mentioned, this is part of we've taken a lot of inputs from other work packages, and the plan was to carry out the analysis for a 20-year period. So all the analysis were conducted within from the year 2019 projected up to 2029. So in the first case, the scenario A, with no smart solution implementation for the Barcelona pilot, what we found out was that there's a requirement of a total of 47 megawatts hour of electricity, as well as 24 megawatt hour of gas, which amounts to a little less than 6 million euros. For the second scenario, which, as I've mentioned, deals with the incorporation of smart solution technologies, here we see a similar or the same demand in terms of electricity. However, there is a reduction in terms of the gas demand. We see a reduction of about 4 megawatt hours, and then of course a total capital investments of a little over 80,000 euros, and then an operating cost of 65,000 euros. Overall, the cost of smart solution technologies implemented in the Barcelona pilots add up to about 5.6 million euros. The results for the Barcelona is still here. We have so a table showing the sensitivity analysis. So we've carried out a sensitivity analysis across different discount rates. And this table here shows some of those values for 2% as well as 3.5%. Actually, 3.5% was the discount rate that was proposed for all the calculations to be carried out. But then we tried to vary that and see how that would change the values or the results that we're getting. Overall, the analysis indicated that the implementation of the smart solution tools for the Barcelona pilot are economically viable with a payback time of 8.2 for that 3.5%, as I've mentioned. And the technologists was also able to save over 53 tons of carbon dioxide emission within just the first year. So this is a massive reduction in the CO2 emission or the carbon footprint. And then, of course, the low income is generated through the participation. So what we'll notice is that there's a lower income as we would expect, and this deals with the low participation in DR events, which is a consequence of the electricity market framework. In terms of the SENGEN, now the transition towards an energy system where the energy generation is entirely based on renewable energy technology, first of all, seem to be economically viable for the DSO stakeholders within the SENGEN system, within the SENGEN energy system, with the DSO obtaining a total economic gain of over 1 million euros. And then that's over the whole simulation period, as I've mentioned, between 2019 to 2039, so 20 years in general, and also holds a social impact, since the transition to a fully renewable-based energy system enables a shift towards a greener energy consumption. It also improves the system energy security and stability because, of course, we see a higher degree of flexibility in order to meet the demand within the system. And also, in the next slide, we'll see a table which presents some of the results from the economic analysis concerning the investment income as well as economic benefits that are gained through flexibility for both the two scenarios, as we can see here. So here, more results we can see for 2.8 as well as 3.5 discount rates. And on the right here, we can see the change in flexibility in the system between the two scenarios. So if we look at the first scenario, which is scenario A without any renewables, we see that over the first about 7 to 8 years, the demand is not met. So that's why we have that negative flexibility. Up until around 2028 or 2029, that's when we start seeing the demand being met, so the flexibility being positive. However, for the second scenario B, we see right from the first year that target or that demand has been met, and as such we have a positive flexibility. So the mismatch is positive in this way, in this scenario. So what can we get out of this in terms of outcome, policy recommendation? Well, the implementation is economically positive for both pilot sites, and also it also provides stakeholder and economical gains. And also the implementation does provide environmental positive results with a decrease in greenhouse gas emission, especially with the Barcelona, as we've seen, and also improved energy security in terms of increase in flexibility. So we see that in the case of the Sengen, right from the first year, for the second scenario, we see that increase in energy flexibility, which is as a result of which results in improving the energy production capacity as well as implementation of smart technology solutions. So overall, we can say, set forward a clear energy transition pathways. Thank you very much for your attention, and of course, I'd like to acknowledge the H2020 InteGRIDy project and Teesside University as well. Thank you very much, and I'll take your questions if you have any for me.
Thanks a lot, Tariq, for your presentation. We have no time for the questions because we are in late. Again, you can write on the Q&A. Anyway, we had some little problem, but at the end we were able to do all the presentation. I would like to thank all the attenders and also the speakers for the very good presentations. So I think it's time to have the break. So thanks everyone, and let's have a break.